want to support that trend. That's
Yeah.
why once research person joins, means we should start.
Physical activities रे हमें आधे घंटा आगुरु hall ले बसतिबा resource person आसले all are eagerly
हाँ,
waiting resource person केतले आसीबे
yes, yes, yes. This is the difference between online and physical. हाँ, ଆପଣ ସାରଙ୍କୁ ପଚାରନ୍ତୁ, ସାର୍ ଯଦି ରେଡି ଅଛନ୍ତି, we can start.
ମୁଁ ready.
Okay.
Okay, sir.
Sir, ଆପଣ introduce कर दियंतु ये
just
मृत्युंजय सर आपण इंट्रोड्यूस करके ये कर दियंतु सर स्टार्ट कर
हाँ.
आଜ୍ଞା
Listen PPT ready करते. Start करना था ready करते.
ସାରଙ୍କୁ ଇ କରି introduce ଆପଣ କରିବେ ନା?
बायोडाटा ऑलरेडी हम इंट्रोड्यूस काल तो करा हैतला ठीक अछि मु जस्ट माने ये रे कहि दउछि
हाँ, ये करथिले खाली ये କରିବା କଥା.
ठीक अछि
Okay, let me start the recording. Okay.
आଜ୍ଞा
Recording in progress.
Okay.
Yeah.
Good afternoon to all. Welcome to this 1 week FDP program. Today is the 4th day, the first session of the 4th day. So this session will be conducted by esteemed Professor R.K. Mishra sir. Sir already taken one session yesterday, so he will continue from that point. And today potential of Mishra sir, you can interact with him and you can boost your knowledge. So now I request Mr. sir, please continue your session. Now floor is yours, sir.
Good afternoon. Please tell me, is my presentation visible and am
Yes,
I
sir.
audible? These two things
Yes, sir.
have to
Yes,
clarify, then I'll start.
sir, your presentation is visible and also voice is clear, sir.
Okay. So now let us start. We will continue with metaelectronics or metaelectromagnetics. Yesterday we saw theory. Today we will mostly discuss applications. Of course, there will be some overlap with theory. Some of the stuff that we discussed yesterday that I will revise, which is essential for today's discussion. So that part also I will revise. And then we'll see some of the applications. Those applications, most of the applications were in our laboratory here at Barampur University when I was there. Okay, so let us start with a realization of metamaterial and metasurface. Yesterday we have seen metasurface realization that I will revise briefly, and let us start with the realization of metamaterial. For metamaterial, we discussed that we require a negative refractive index. To get refractive index, as we know, refractive index is square root of permittivity and permeability. And we are mostly acquainted with permittivity or dielectrics. We rarely use, many people use permittivity or dielectric than magnetic materials. So rarely magnetic materials are used by some people. So we'll start with the permittivity. And we saw yesterday that naturally occurring metals act as plasma. Or they are in the second quadrant where epsilon can be negative or permittivity can be negative. Now, how to generate this plasma, artificial electric plasma, how to generate it? That is the question. So, theory we have seen. Now, let us look at the application of that theory for generating the plasma. What we will do is what has been done in the past, that I will try to revise and discuss very briefly. This is taken from one of the papers of Pendry. who realized artificial electric plasma. Now, what he did is he took arrange of periodically arranged rods, conducting rods, very thin compared to the wavelength, and spacing between two rods is also not very large compared to the wavelength. So the diameter of the rod of each rod is 2r, spacing between two rods is a. So you can also say that if I take midpoint between two rods, then the midpoint between the next two rods, their distance is a. The electric field is oriented along the rod. Rod is oriented along z-axis, and in the x-axis, x or y-axis, xy plane, the base of the rod is there. So the vector, propagation vector k is in the xy plane, rod orientation is in the z-axis, electric field is along the rod. So this is the arrangement for artificial electric plasma. Now we'll see how or the principle of getting the negative permittivity from this arrangement. So what we'll do is we'll first find out the fill factor. Fill factor, when we try to find out the fill factor, we locate the rod at the center of the cell. Our cell size is A, but the distance between two rods is A. Therefore, the cell size will also be A. At the center is the rod of diameter 2r. And then the fill factor, there are two fill factors. If you add them, F1 plus F2, that will give us 1. The fill factor 1, F1, is defined as pi r square by a square, which means the area of the base of the rod divided by area of this cell, unit cell area. So that is pi r square by a square. Now F1 plus F2 is equal to 1. So for the space, the fill factor is F2, which is 1 minus F1. So we get two fill factors, F1 and F2. Next. Now, with these two fill factors, what will be the permittivity? How to find out the permittivity of the artificial dielectric that is generated by using these rods. Now, if you look at the structure in the xy plane, they are symmetric. So, but in the z direction, there is no symmetry. In the z direction, rod is oriented, but in the xy plane, whether you go in the x direction or you go in the y direction, the arrangement is same. Therefore, the dielectric constant or the permittivity will be same in the x direction and in the y direction. Therefore, but it will be different in the z direction. Therefore, the dielectric constant or permittivity will be a tensor given as a matrix in which the matrix elements will be the first element will be epsilon xy. Similarly, in the second row, the element will be epsilon xy. Actually, it is epsilon yx, but because of the symmetry, it will be epsilon xy. And in the z direction, let us take it to be epsilon z. Now, electric field is in the z direction. So interaction is in the z direction. So our interest is only in the epsilon z, not in the epsilon xy. Next. So we have to find out what is epsilon z. Now we know what is form factor, we know the form of the permittivity, and in the permittivity form, our interest is in the epsilon g. So what we'll do is find out epsilon g. For finding out epsilon g, it is acting like a plasma. So since it is acting like a plasma, the arrangement is like acting like a plasma fluid. So first we have to find out the electron density. Electrons will reside only on the metal part, not in the free space. Therefore, on the metal part, so we'll find out the effective electron density because this is not a continuous distribution of metal. So we'll find out the effective electron density N effective, which is equal to N into the have F1 or the field factor, first field factor. So that is N effective. Then, since the electrons are confined to thin wires, which are acting like having different effective mass, so the whole thing will have a different effective mass. M effective is equal to mu 0 R square E square N. E square is the charge of electron, one electron charge. Then by 2 log natural A upon R. Then once you know N effective and mu effective, you can use the Joule model to find out the effective permittivity epsilon z, which is epsilon effective omega, which will be a function of frequency, angular frequency. That is given as 1 minus omega square p effective. Omega square p effective is plasma frequency, effective plasma frequency divided by omega into omega plus j gamma. Now omega square p effective is n effective into e square by m effective into epsilon 0. So if you put those values, n effective value, m effective value, then that will give you 2 pi c square by a square log natural. So once we know what is our requirement, what will be the is A, what is the required is E, then we can find out what is A and R using this formula. So that is one design. Then there is another case which is optical plasma. In this, what we do, instead of taking rods, periodically arranged rods, we take these planar layers. So two different dielectric materials. One the material is epsilon 1, other material dielectric constant is epsilon 2. We take their layer. So one after alternatively epsilon 1, epsilon 2, epsilon 1, epsilon 2, they are placed alternatively and of the same thickness, same size, everything is same, except the dielectric constant is changing, that we use. Now, if you use that way, then if we look at the dielectric constant, then again dielectric constant will be the tensor, because along xy plane, uh, the electric field is in the z direction. So in the xy plane, that xy plane will be the electric field components will be considered parallel. So epsilon parallel. So both will be same. Xy plane epsilon. So epsilon xx is equal to epsilon yx is equal to epsilon yy. So those will be epsilon parallel, and in the z direction it will be epsilon perpendicular. Now, the periodicity here is assumed normally A has to be very small than lambda, that is A should be in the sub-wavelength region. Then we know F1 plus F2 is equal to 1. Now consider the electric field in the xy plane. If the electric field is in the xy plane, then E is equal to E1 is equal to E2 in the x or y direction. E1, E2 are x direction, y direction. So E is equal to E1 plus E2. Similarly, D is equal to F1 D1 plus F2 D2. Now what is D? D is epsilon E. So put epsilon E on the left side, right side for D1, put epsilon 1 E1, for D2 put epsilon 2 E2. Then we know E is equal to E1 E2, so cancel that out. So epsilon is equal to F1 epsilon 1 plus F2 epsilon 2. So epsilon parallel is F1 epsilon 1 plus F2 epsilon 2, which is the weighted average of epsilon 1 and epsilon 2. So that is how you find out epsilon parallel. Now we have to find out epsilon perpendicular. For that, again, if you look at this, D is equal to D1, and that is equal to D2. Now E effective is equal to F1 E1 plus F2 E2. E effective is D by epsilon effective. Then E1 is D1 by epsilon 1. E2 is D2 by epsilon 2. Put these values. Finally, you will get 1 by epsilon effective is F1 by epsilon 1 plus F2 by epsilon 2. From that, we can find epsilon effective, which is epsilon perpendicular, that is equal to epsilon 1 epsilon 2 divided by F1 epsilon 2 plus F2 epsilon 1. So this is basically a weighted harmonic mean. So epsilon perpendicular is weighted harmonic mean. So these are two plasma realization of plasma realization of once you go to plasma, once you realize the electric plasma, there will be a frequency region where it will be negative. Epsilon permittivity will be negative. Now, how to get the permeability negative, the magnetic property, how to get that magnetism from the conductors, using conductors, how to get magnetism. It is extremely difficult to realize magnetism unless you have magnetic materials, ferric materials or nickel, cobalt, and unless we have those materials, it is extremely difficult to realize magnetism. Now, how to realize magnetism with normal metals? Normal any metal, if you use any metal or a conductor, any other conductor, then how to realize magnetism? So what we do is first take a disk, a conducting disk, which is the left side. Look at the three pictures. Look at the left picture. So consider a conducting disk and apply a magnetic field which is out of plane from the disk. So disk has a plane perpendicular to that plane is the application of the magnetic field. If we apply a magnetic field in that direction, then that magnetic field next later, and then that magnetic field will induce a circular current. Why? Because according to Lenge's law, magnetic field will be opposed by this disk, by this conductor. So it will oppose the external magnetic field that there will be induced circular current. Now this disk being conductor, the current will be mostly at its edge, outer side. The current do not penetrate into the conductor, so it will be mostly in its outer side. So current is mostly on the edge. Now, this is basically a dimagnetic thing which is very weak. So, weakly dimagnetic mu is less than 1. So, this is not going to solve our purpose, but we'll develop on this next. Now, since current is on the outside, there is no point of using uh, other portions of metal or other portion of conductor, which will lead to higher conductor loss. So, remove those portions where there is no current. Remove those portions. So, effectively, we get a ring. In the ring, that is confining the current. So, we get a ring from the disk. We get a ring. So at the edge of the current disk, so we get a ring which gives the same response or similar response to the disk. Now here also the induction response is non-resonant. Here since the induction response will be there, there is only induction response, so there cannot be any resonance. Again, weak magnetic field. Now to get resonance, we have to have a capacitive effect. So what we will do is we cut the ring, make a small cut, not a large cut, small cut. If we make a small cut, then across the cut there will be charges. On one side there will be positive charge, other side will be negative charge. Therefore, there will be capacitance. If it is a large cut, then the capacitance will be small or negligible. Why? Because C is equal to epsilon A by D. If you increase D, D is the cut size. If you increase D, C will be smaller. So that will be negligible. So make a small cut, so we get sufficient capacitance. So the split will introduce capacitance. Metal, as usual, will give us the inductance, and we have got inductance and capacitance. So inductance and capacitance means LC circuit. So LC will make it resonant with omega 0, or the resonant frequency is equal to 1 upon root over LC. Next. Next. Now on left side is that. Now there is a problem. Because at the cut we have a plus and minus, a plus charge and minus charge separated by a small distance that is acting like a dipole. So it is like acting like an antenna. The moment it acts like a dipole antenna, the strong dipole antenna that will be dominating the magnetic response will lose the magnetic response to a large extent. So that is to be taken care of. So to take care of that, we use another split ring in the opposite direction. The split is in the opposite direction to the uh, split of the outer ring. So there are two dipoles on two rings, but in the opposite directions. So the charge distribution is different in the outer one. The upper side is positive, in the inner one, upper side is negative. So this since the charge distribution is different, they will cancel out. The antenna effect will be cancelled out. Therefore, that is one point. Second point is there are two capacitances. So they come from two rings separated by gap. So this will give us a better magnetic response. So ultimately we arrive at this point which will give us better magnetic response. If we look at the circuit, what will be the equivalent circuit? We have L, definitely, then two capacitances. We have A, then we have two capacitances, then we have R. Because we are using conductor, so that will have resistance. So we have R. So we have an equivalent RLC circuit for which omega 0 will be root over of 1 upon L plus R by j omega into C. Next. So accordingly, you can find that. So now that can be arranged in periodic fashion to get magnetic plasma. So now we have got magnetic response earlier. Now we get magnetic plasma using arranging them in periodic fashion as in case of rod. So you can use Lorentz law or Period law to find out how it will vary with frequency. The how mu will vary with frequency that can be used there. Next. Now, how to get metamaterial? Metamaterial has mu effect, mu is negative, epsilon is negative. So first generate the negative epsilon, next, then generate the negative mu. Now epsilon and mu, they are negative over a certain range of frequency. There will be a band of frequency when there is an overlap of negative permittivity and over negative permeability. So choose that region next. So add these two. If we add these two, then there we get a region where both are negative. Epsilon is negative, mu is negative. There we get negative refractive index, or we get metamaterial. So this is practical realization of metamaterial. Next. This shows instead of circular ring, we can also use square ring. This is an example of fabricated rings, and on the back side of the ring there are rods or planar rods, which is strips of metallic strips. So those are exactly on the back side of the ring. Next. Now, what are some of the applications? Because that is the main focus today, application. First is if you use metamaterials, then Doppler effect gets reversal, which means if the source is approaching you, instead of frequency getting increased, frequency will decrease. For example, one application I will tell you. Suppose you are in a war and your plane is going to the enemy zone, and your a plane has metamaterial on its surface. So when it goes to the enemy zone, the radar will see that the plane is going away from the enemy zone. Why? Because the frequency has decreased. Reversal, because of Doppler effect reversal, it will feel as if plane is going away from the enemy zone. So it will be difficult to detect it. And then the Gauss-Hansen effect is reversed, which means what happens is generally the point where you incident the light or where you incident the electromagnetic field, from that point it gets reflected. That is the usual RHM phenomenon. But in this case, it will be shifted. So reflected beam will be shifted from the point of incident beam. From where incident beam is being incidented, from that point it will be shifted. That is called a Gauss effect. Now, because of this shift, if you are using a radar to detect something, detect a material, detect an object coated with this metamaterial, then the exact point you will not know, because the point from where it is getting reflected is at a different location, actual location. It is not getting reflected from the actual incident point, it is getting reflected from a different location, so it will be difficult to locate the object exactly. So that is another application. Another is Cherenkov radiation reversal that I will not discuss. Then Snell's law reversal, some of the applications we will see later. One application is you can use a concave lens to get convergence and convex lens to get divergence. That is one application. Flat lens we discussed yesterday. Superlensing. What happens is if you use a normal lens, then the incident wave vector, you can see it as having two components, the perpendicular component and the parallel component. The perpendicular component passes through the lens. The parallel component gets attenuated. Being parallel to the lens, it gets attenuated. But if you use this metamaterial, the parallel component also passes through without attenuation through the lens. Therefore, the lensing effect is enhanced. This is called superlensing. So the diffraction, because of the parallel portion, we get diffraction. The diffraction limit is overcome. Then cloaking means hiding, that we'll see later. Next. Now, with those applications, let us leave out for the time being the metamaterial and we'll come back to meta surface. Give me a minute, I will take some water. Okay, yesterday we discussed how to handle the wavefront, how to manipulate the wavefront. But I skipped this one deliberately. This portion I skipped. And now what happens here is how do you manipulate the wavefront? What is the principle involved? Simple physics or simple logic. Consider a wedge-shaped dielectric material or a wedge-shaped you know, mm, lens, etc. Now, in the wedge shape, at one end you have a larger distance. Left end, you can see the left end, you have a larger distance. At the right end, there the distance is minimum or zero. At the right hand tip, the distance is minimum or zero. Now, incident a wave normally, incident any wave normally onto this wedge from the bottom. You can do it from the top also. The principle remains same. From the bottom. Then what will happen? The wave will come out of this wedge first at the rightmost point and come out from the wave at the last at the leftmost, which means the phase front is slowed down at the leftmost point and it comes out with the same speed at the rightmost point. So that is going to give a tilt to the wavefront because at one point it has come out already, at the other point it has not come out, at the other point it will come out later. So, and it will be tilted towards this side. Next. So it shows how the tilting will be there. The tilting will be towards the edge, which has the least distance. So from the maximum distance towards the least distance, the tilting will be there. Next. So that how to realize that, how to uh, realize this tilting or how to realize this weight setting. what happens actually in this wedge. So at one side phase is slow, at other side phase is fast. That is what we are seeing. Phase is slow means it has the larger distance. Larger distance means the more the distance, the more is phase. So that side you will get more phase, other side you will get less phase. So from high phase to low phase, it is the tilting is from high phase to low phase. Now, how you will get that? Take an antenna. Consider any antenna. I am taking a rod antenna or a linear antenna. Incident electric field, which is parallel to the antenna, onto the antenna, and draw the phase and amplitude of the antenna. So that you can see on the left side figure, top left side figure, you can see the amplitude is maximum at around 4.4 L by lambda. L by lambda means the length of the antenna is varying, lambda being fixed. If you keep on changing the length of the antenna, there will be a particular length at which it will originate. The amplitude will originate. That will be the maximum. So consider that point, and at that point, consider what is the frequency. Sorry, what is the page? So you can find out the page, and you can see as we keep on changing the lambda, as we keep on changing the length, the phase is changing from left to right. As you keep on increasing the length, the phase is changing, and so long as the amplitude is above 0.7 means, which means half the amplitude is transmitted, then we can accept that those region we can accept. So this is one. The second is what is the phase difference? If we use this, what is the phase difference? You can see the phase difference is maximum phase to minimum phase. The difference is around pi using this. Now, how to get the required phase difference over a surface? Over a surface, we want to get a required phase difference. Suppose we require 8 pi phase difference. And suppose we have an antenna which gives us 2 pi phase difference. Then what we will do is we will use this antenna, we will use the principle of wedge. So you can see the wedge shapes in the below. So for the first wedge, the phase difference is from 0 to 2 pi. My antenna is giving 0 to 2 pi, so first phase is 0 to 2 pi. Then 2 pi is same as 0, so come down to 0. Then repeat the same antennas 0 to 2 pi, come down to 0, 0 to 2 pi. So that way you repeat 4 times, so you get 8 pi. So how many pi you require accordingly? Use this wave shape principle. So arrange the antenna according to your requirement. So if it is linearly 0 to 8, you will do this. If it is 0 to 4, then maybe 6 to 3. So this way you will arrange accordingly, you will make arrangements. Next. Now, we are going to use the principle of reflection. So some principles we should remember always about regarding reflection. The first principle is, suppose there is a reflection between two dielectric interfaces, then it will be the reflected beam will be either in phase or out of phase, so 0 or pi with the incident beam. If N1, the past medium, dielectric constant is less than the second medium, then the phase is pi. If in the past medium dielectric constant is more than the second medium, then it will be 0. But if you go to a PEC, perfect electric conductor, always it is pi. The reflected thing is always pi. And in between these two, there are lossy materials. Next. In the lossy material, always the reflection will be between 0 to 2 pi. So if we use lossy material, which is the case that we are going to use, there always it will be 0 to 2 pi. Between 0 to 2 pi, you can realize 0 to 2 pi. If you require pure pi, what you can do? If you require pure 0, what you can do? And that we have seen now between 0 to 2 pi any value. For that, we require lossy material. Next. Now, let us remember the generalized Snell's law that we discussed yesterday. Normal Snell's law is n2 sin theta t is equal to n1 sin theta I. T and I are for transmitted and incident waves. Now, generalized Snell's law is what happens at the boundary is between the two dielectrics. At the boundary, what we have done is we have given a phase difference. We have given a gradient phase. Now, if the phase is zero, actually n2 sin theta t minus n1 sin theta I is equal to zero. The discontinuity is zero. There is no discontinuity of phase. But if there is a phase discontinuity, then this will be proportional to the phase discontinuity. But the left hand side you have is a unitless quantity. Right hand side it is proportional to the grad phi or proportional to the phase gradient, but phase gradient has a unit. So its opposite is 1 by k0. So therefore, for the constant, you take 1 by k0. So that gives us the generalized Snell's law. Next. Now this also we discussed yesterday, so let me discuss it in slightly more detail. Suppose we want a frequency or a effective length of the linear antenna. So we take the antenna effective length to be 2L. So lambda effective, we take the effective length to be 2L. Now in that, what happens is on the left hand side of that, suppose we have the negative charges accumulated, and on the right hand side we have positive charges accumulated. So from positive to negative is the arrow showing the electric field. Now there can be another case in which in this module there will be positive charge on both the sides, there will be negative charges. So from the positive to negative, we have the electric field. Now from positive to negative is L distance. That is lambda effective. So that will be equal to L. So we have the same length, but there we can generate two frequencies or two wavelengths. Now to realize it in the form of antenna, what we usually do is we fold it from the center. So take 2L length, then fold it from the center. So you get a V-shaped antenna. That is what we discussed yesterday about V-shaped antenna next. And this part we discussed yesterday, so I am leaving it out except this portion next. Electric field, what will be symmetric, what will be vertical, that we have discussed. This I have discussed next. Next. Okay, now the arrangement we have seen for the arrangement, linear arrangement, we have seen for the linear arrangement, look at the left hand side figure. So it is from 0 to 2 pi. Suppose it is over a period of gamma. So variation is 2 pi over a period of gamma. Therefore, d phi by dx, which is used in the generalized Snell's law, right hand side, k0 d phi by dx. So d phi by dx of the gradient of phase change is 2 pi. 2 pi is the total phase change over a length gamma. Therefore, gradient is 2 pi by gamma. So d phi by dx is 2 pi by gamma if we take this arrangement. Look at the right hand side. What we do usually, what is done in this paper, light propagation with piezeless continuity paper, use group. So in that group, or Capasso, main is Capasso. So in Capasso's group, what they did is they took this along the x-axis. This arrangement is along the x-axis. Then along the y-axis, the uh, shape is preserved, that you can see. Since along the y-axis shape is preserved, there will be no phase change in the y-axis. So d phi by dy will be equal to 0. Along the y-axis it is 0. d phi by dy is 0. Along the x-axis, we know 2 pi by gamma. Next. Now comes the efficiency trade-off. Now, ideally, what we require is the phase change or the phase gradient should be continuous. But we are putting antennas at discrete places, separated from each other. Now, if you want continuous, then the antennas should overlap each other, and in that case, you will get nothing because the antennas are overlapping on each other. Same phase will be repeated at one point. There can be 5 phases, so that is of nothing. So, depending on the space available to you and the gradient required by you, you have to decide the number of antennas that can be put within that phase or within that space, which is a difficult process because if you reduce the number of antennas, then the efficiency will go down. So we are using here 8 antennas. In the top example, we are using 8 antennas. So this will give you a very good result if instead of 8, if we can use only 4 antennas, the space is limited, we use only 4 antennas, then the result will not be so good. So efficiency will go down. So depending on this available space and arrangement of antennas or the structures in its cells, we can uh, uh, have the efficiency to be better or less efficiency. Now we considered V antennas up to now because that was the first thing that was proposed. But there is no hard and fast rule that you will always use the V shape. You can use any other shape that we will discuss shortly. Next. Now, when there you can see the results here for using V-shaped antenna. You don't use any V-shaped antenna, so no phase gradient. If you don't have any phase gradient, we follow the curves that are the black curves on the left hand side for refraction. On the right hand side, it is for reflection. So they follow the normal Snell's law, particularly on the right hand side, you can see it is from minus 90 to 90 for 45 degrees slope. So theta I is equal to theta R is completely verified there. But if you give this phase gradient, then the red curve shows us what is going to happen. The negative refraction is clear, the anomalous refraction is clear because it is below the curve or the black curve, it is negative refraction. Similarly, here it is below the black curve, it is negative reflection. Next. With this much information, now we'll come to the synthesis of the meta element. Instead of V antenna, what other shapes can be there? I will confine myself to the shapes that we discussed or designed in our laboratory. Uh, Next. Oh, this is okay. Look at the leftmost part. What we see is a ring. So it is like a ring antenna. Near it are an array of ring antenna, 4 ring antennas, and array of ring antenna. What we are considering here is reflection phase for the ring antenna. You can see it is between 150 to minus 150. So about 300-degree phase shift is possible with ring antenna. And for the magnitude, you can see it is mostly above 0.707. Here you can see it is above 0.78 when you take the array. So it is above 0.78. So this is a good candidate. 0.78 means half power law that is accepted. That is acceptable here. That is applicable. So half the power is lost. Maximum half the power is lost. But mostly it is above 0.98. except for a small zone where you have the deep. Similarly, for the second, we have a cross, then array of cross, similar results. Then we have a Jerusalem cross, an array of Jerusalem cross, almost similar results. So any of these one can use as the meta element, including the V, but depending on your requirement, you can use any of these. What we did is consider this, then we developed our own structure, which we called a modified Jerusalem cross, which looks like this. The inside figure that you can see in the top left side, the inside figure is the Jerusalem cross. If you look at it, the phase variation is from 150 to minus 150 for different angles. Phi is equal to 0, 15, and 25 for different angles, but the variation is same. Only variation remains same, although angles are different. Um, and the amplitude, if you look at the amplitude is above 0.98. So magnitude of reflection is above 0.98 for this structure. And the current distribution, you can see mostly the current is distributed inside the ring. So this is basically the Jerusalem cross, which is modified. So what we do is we take a ring, and on the ring, at the center of each arm of the ring, we put a T. So that gives you a Jerusalem cross type of thing. So this is, and the maximum current is always at the center of the ring. And at different, this is for the top left is for different angles, but for different frequencies also we saw that the reflection phase variation is from minus 180 to about 175. So almost 360 variation, 300 to 360, 350 to 360 phase variation is achievable. We can achieve that much of phase variation. Reflection magnitude, there is no problem. It is everywhere it is above 0.95. So this is an excellent structure that we adopted for our research or our work. All the work that we did, we adopted this structure completely throughout our work. Next. Now let us use that structure. Why we will use that structure, for what we are going to use that structure. First thing is we will go for a flat lens. That was the question. The lens was the question in case of the metamaterial. So in the metamaterial, we designed a lens, but it is a thick lens. Instead of a thick 3D lens, we have to go for a planar lens. For the planar lens, what is to be done? From the surface, it is to be focused. We have to focus it. Now, what we did is we started uh, fabricating a surface, designing a surface onto which we will incident normal waves. So, if you incident normal electromagnetic wave, you expect that the reflection will come back in the normal direction. If the incident is in the normal direction, usually it should come back in the normal direction. But we do not want that. We incident in the normal direction, but the reflected wave is not in the normal direction. It has to be in some other direction. Now we have seen from the wedge, the principle of wedge, that from high phase to low phase, the tilt has to be from high phase to low phase. So what we did is first we tried to see whether that is happening or not. We designed or distributed these Jerusalem crosses of different size. Why different size? As the size changes, the phase also changes. Corresponding phase changes. A by lambda, you remember, or L by lambda, you remember that figure? L by lambda. L by lambda, as you keep on changing L by lambda, so with lambda constant, if you can keep lambda constant, vary L, or keep L constant vary lambda. So for any lambda, if you take any lambda, take constant lambda, then vary L. L means the size. So if you keep on varying L, the phase will change. So that principle we are using. So we are distributing it over a planar surface. So how it is distributed? Leftmost is pi, then rightmost is minus pi. So pi to minus pi, then again we distribute it from pi to minus pi. So what we expect from positive to negative, from high phase to low phase, the tilt will be from high phase to low phase. We have seen it for three distinct frequencies, 9.5 gigahertz, 10 gigahertz, and 10.5 gigahertz. These are the three simulations because this you cannot measure it experimentally, you cannot see the wave. Experimental is different. In the experiment, you can see the radiation pattern. So from that we will get that we will see later. But from the simulation, you can see it is from the left to right, plus pi towards minus pi. The beam is tilted in all these three cases from plus pi to minus pi towards minus pi. From left towards right, it is tilted. Now we have to use this principle for the lens. Next. So for the lens, what we did is use the same thing, plus pi to minus pi. First arrangement is from plus pi to minus pi. So that will tilt it from left to right. Second arrangement is from minus pi to plus pi. So that will tilt it from right to left. So ultimately there will be focusing. That you can see the top view of the simulation. From the left one beam is coming, from the right one beam is coming, they are converging. So that is how you will converge it. The top view and this side view, both you can see the beams are coming and they are converging from two sides of the flat lens. They are coming and converging as if it is a normal convex lens as it comes from two sides and converges to a focus point. Here also same thing happens. They are coming and converging to the focus point. Now what we did is we saw the radiation pattern because the simulations you cannot see, but the radiation pattern we can see. So we are seeing the radiation pattern. If you look at the radiation pattern, 2D and 3D patterns, you can see these are all converging in the vertical directions. The beam is in the vertical direction. In the since the beam is in the vertical direction, you can say it is mostly converging. So if you incident any ray, that will be focused in the vertical direction using a flat lens. So this is something that we realized in our laboratory. Next. Then give me a minute. There's a figure. बंद कर दो सबको सेव तो ये कर दो give me a minute I have to sneeze
Yes, sir. Sir.
हाँ ଗୋଟେ minute ତଣ୍ଟି ଲାଖିଗଲା କଫ ତ
Again, sir.
¿Cuál tenemos? Start करूया. मार देंगे. Figure transfer. Next month. Okay, now we will consider another structure. In this structure, we have taken a hexagon. Within the hexagon, we have put an edge. So the dimensions are given here. Unit cell dimension U, or what we called earlier A, is 7 millimeter. The unit cell contains a hexagonal ring. Arm length is A. Apothem is L. They are related by hexagonal geometric relation. Inside the hexagonal ring, there is a H-shaped inclusion. Side length is HS, which is A minus 0.2 millimeter. Separation V is separation is 2V. Width is 0.5 mm. Gap is 0.25 mm. We used FR4 material for which epsilon r is 4.2 to 4.3. Yeah. Thickness of the material is 1.6. And as a function of apotheme of the hexagon, which is L is actually equal to V plus G plus W. The magnitude and phase of the reflection coefficients are obtained. Next. Okay. Now, once you distribute this structure over the surface, For example, let us we want it's a phase change or phase gradient between two consecutive cells. How to find that? D phi is equal to 2k0 u sin theta. So depending on what will be your theta and what is u and k0, you will find out what is d phi. So if you put that those values, that gives you 43 degree. Theta, what is theta? Theta is the tilt angle of the metallic bump that we will discuss later. But theta is an angle. K0 is free space wave number. U is the size of the unit cell. Metallic bump, what we'll see is we take a ground plane. On that ground plane, we have put a metallic bomb. So metallic bomb is like a triangle or a trapezoid. You put a trapezoid on the ground plane. So the trapezoid makes an angle theta with the ground plane. So based on that, we design this. So 43 degrees is d phi. So now we require how the total is 360-degree phase shift. So 360 by 43 is equal to 8. So you require 8 number of unit cells over the bomb. At least 8 number of unit cells or more than 8 numbers is good. At least we should have 8 numbers of unit cells. Next. Now, if you have uh, polarized electromagnetic field, this is the structure that we'll use. If we have next electrically polarized field, this is the structure that we'll use. And if we have circularly polarized electric field, this is the structure that we are going to use. So these are the three structures that we use depending on the polarization of the electric field. Next. Now, this shows for these three structures, circular polarization, linear polarization, and electrical polarization. Once you make the surface, then the phase amplitude resonance responses for the structures, each structure is shown here. It varies from 150 to about 200. So 350, 360, very close to 360 variation in phase is there, and it is above the amplitude is above 0.99, which is definitely acceptable. So if you design a surface with this, that is acceptable. That surface I will tell you where I am using, where we are using this surface. That I will show you later. Next. That surface we use actually in carpet work. We'll start with a carpet work first. Then we'll come to that surface using that surface. In the carpet work means you have to hide. Something is to be hidden. So now, suppose you have your aeroplanes, fighter planes, at some location which you do not want your enemy to find out. Now, on those fighter planes, before the fight, if there are absence of fighter planes, you will have a plain ground. It will act like a metal. Ground usually acts like a metal. So you will have a plain ground. If your enemy incidents electric field onto the plane ground, the reflected or enemy incidents electric field onto your field where you have the planes, usually if there are absence of planes, it should get reflected, normal reflection. So field distribution will be like this. This field distribution they will observe. Now suppose you have the plane, it will be like a bomb on the on ground. So it is a bump that you can see this white space is a bump. One plane is there or one hanger is there to contain the plane. So if you have the hanger there and you incident electromagnetic field, your enemy incidents electromagnetic field onto that hanger, the reflected field will be scattered in the all possible directions in the reflection direction. All possible scattering will be there. So from that, the enemy will know that we have a hangar there, so there is a possibility of aeroplane. They can bomb that, so they can eliminate that hangar easily. Now, what we do is we cover this hangar, which contains the plane, with a metamaterial. Talking metamaterial next. So we put a metamaterial, cloaking metamaterial, we call it a carpet. As if we are putting that bomb or the hanger under the carpet, we put a carpet on this metamaterial, we put a metamaterial. If we put a metamaterial, you can see now the reflection is almost similar to the reflection from the metallic ground plane. So the enemy will not be able or will be confused whether there is a hanger or there is absence of hanger. This is one of the applications where you use the clock bumping, where you clock the bump. This is one of the applications. But the problem here is if you put metamaterial, it will be so bulky, so large that its weight will be very large and very high weight. So the hanger may not be able to withstand that weight. That is the problem. Next. Here we see the thickness. With if you keep on increasing the thickness of the clock, then there will be better um, clocking. If you decrease the thickness of the clock, there will be not where the clocking will not be so good. This graph show that. Next. And now instead of using that bump, you can see we are using we are proposing to use this hexagonal thing, this hexagonal distribution on one plane. And the plane is in the form of a bump. So that will cover the bump. The plane will cover the bump. The electric field distribution you can see. Based on this electric field distribution, there will be again reflections. Next. Now, if you incident normally onto those at 9 gigahertz, you can see the top left is normal incident and reflection from the ground plane. The top right is normal incident and reflection from the ground plane when there is a bomb. So when it is reflected, it goes in two different directions that you can see. But the when the clock is there, the direction is almost in the direction in the top direction. Next, this is at 9 gigahertz, then this is at 9.5 gigahertz. Next, this is at 10 gigahertz. As you increase the frequency, it is more like a straight going up. Lower frequency, it's like small discrepancies are there. High frequency, it goes as if it is going up in parallel direction. Next, 10.5. So this shows all the four are taken together at one point. So the best result is at 10 gigahertz, 10.5 gigahertz. So depending on what is the frequency, we have to design the carpet. Next, hexagon size, etc. We have to take accordingly. This shows the scattering from the bomb. You can see the scattering. Top left shows you the electric field of the incident and scattered electric field taken together at 9 gigahertz. Top right takes you the scattered field only. Similarly, at 10.5 gigahertz incident and electric as the left. Now you see, those are the simulations. But in practice, we see the electric field. So here, these are the fields. In the A, D, and G, these are from the metallic plate. If you have metallic plate, the reflection at 9.5, 10, and 10.5 gigahertz are shown on A, D, and G. This is going upward in the vertical direction. The beam direction is vertical. Now, when the metallic bump is there, it gets sprayed. Instead of vertical, pure vertical, it gets sprayed in the vertical direction. Now, when you have the bomb and the clock on the bomb, then again the spreading is limited. It goes down, it gets limited. That is what we see here. Next. This is another thing, creating beams with arbitrary polarization. So you create beams from a surface with different polarization. What we do is we take two units, the unit 1 and unit 2. So unit 1 is a row, unit 2 is also a row. Unit A, unit B. Two rows they are laterally shifted. The rows are laterally shifted. So the two rows of elements in the unit cell, they will create two orthogonal polarization components with 90-degree phase difference because this lateral shift is such that between the top row and the second row, first row and second row, the phase difference between two elements is the phase difference between the first element is 90 degree. We ensure that D is 90 degree. So the phase difference is 90 degree. So the polarized wave that you get linearly polarized, but with different phase. Since phase are different, what you can do is two different phases. You send two information with two different phases. So there will be no interference, same frequency you are using, but because of the arbitrary polarization and phase difference, you can send more amount of information at different frequencies by arranging this structure. Next. Then we'll come to the enhancement of gain. So there what we do is conventionally we consider a parabola. At the focus of the parabola we keep a horn, and from the horn we incident onto the parabola. They are converged, or they when they get reflected they converge, increasing the gain. Instead of that, what we'll do now is, instead of the parabola we'll use a planar surface. On a substrate, the substrate there is a ground plane, and on the substrate there are antenna elements, and they are distributed in such a manner that the phase of the antenna elements will resemble the phase that is getting reflected from different points on the parabola. And so the parabola is effectively replaced. Next. Here we saw what we have done is the phase that we have quantized between 182 to minus 180, that phase the region that we have quantized into different quantum numbers. Then we arrange that on a circular ring, on a circular patch. So consider a circular surface. On that circular surface, you divide into different rings, and rings are each ring will correspond to one phase. Distribute the elements on each ring. So that is shown in the left side, what is the phase, quantized phase, and on the right side we show the arrangement of rings, practical arrangement of the rings. Next. And you can see if you use this and take the measurement of the S parameter with the ring, with the antenna, and normal antenna, the matching will be not better compared to the antenna with this surface. So if you put an antenna on this surface, that will give you better matching. S11 will be better. Next. Now you will use that principle to get a high-end meta-surface antenna. What we do is take that plate, the ring plate on the bottom. Above that, put a microstrip antenna. From the microstrip antenna, illuminate that bottom plate. So the reflection from the bottom plate will be converging. That is how the gain will increase. Next. It shows the practical antenna, designed antenna, and the top antenna is on the left side, middle is the designed antenna, right side is the experimental arrangement, measurement that we have done. Next. This shows you the gain. The red line that you see, clear red line, is for a normal antenna, microstrip antenna. And the dashed lines above, the green and blue dashed lines, are for the gain enhancement. You can see the gain is enhanced by about 10 dB. 10 dB enhancement of gain is possible, that you can see from the top left figure. Next. And once we are able to generate a high gain, then we thought that let us use this high gain antenna to generate circularly polarized antenna. So what we did is we took the high gain antenna as it is, then above that we put a surface, a meta surface, which is capable of converting the linear polarization to circular polarization. So another meta surface we used above the antenna. So for converting linear polarization to circular polarization, So that converted the linearly polarized wave to circularly polarized wave. Next. Now for that metal surface design, we knew that how to get circular polarization from microstrip antenna. Take a square microstrip antenna, cut its two opposite corners, make small cuts in the two opposite corners. Same principle used here for rings. So instead of the microchip antenna, we put it inside a circular ring, and in that we use as if we are using a antenna and cutting its corner. So you can see the second figure, figure A. Above, below is the designed antenna, and cross polar polarization you can see on the uh, uh, right side, top right side. You can see cross polar reflection and copolar reflection. So both are equally there. Therefore, axial ratio will be below 3 in the frequency range of 9.5 to 10.5 gigahertz. So for that, we got good axial ratio and we got good gain. Next. So this is the ultimate high gain CP cavity antenna. So the antenna that I showed you, that is here. The complete arrangement is shown here, where we have got very high gain experimental results. You can see on the bottom left side, you can see the experimental results showing the high gain. The bottom line, the dashed line, the green dashed line, is for the normal microstrip antenna. Here, with the proposed antenna and the simulated antenna, you can see the gain is very high, at least 10 dB high. That gain you can see. Next. Then once we got that, then we thought that there are situations where you require the information to be sent in different directions, multiple directions. So what we did is we thought that let us send it in four directions. I'll show you the uh, application, but we thought let us send the direction of the antenna beam. Instead of having one main beam, let us have four main beams, at least four main beams. So we thought of a card beam antenna, four beams. So A shows the total surface over which we are distributing the meta elements or unit cells of the meta elements. That surface we divided into four parts, four equal parts, four quadrants. Each quadrant will send a beam in one direction, in a particular direction. That is what we did. And the phase distribution for each quadrant, for the first quadrant is shown. First quadrant is showing, you can see the beam. For the first quadrant, that you can see the first beam. Then the second beam is for second quadrant. Third beam is for third quadrant. Fourth beam is for fourth quadrant. So this way we generated four beams. Next. From one antenna, you can see from the center, it is going in the four directions. Four beams are going there. Next. We generated that. Then, once we were successful with that, then we thought that why not use circular polarization also? Generate four beams. And above that, put a linear to circular polarizer at the top of the antenna. So that is what we did. So we put a linear to circular polarization. A is the phase distribution on the surface. B is the element distribution according to that phase. Then C is the linear to circular polarizer. So the B will be at the bottom, C will be at the top. In between them, there will be microstrip antenna exciting the surface B. So whatever gets reflected from the surface, that will go through the C and it will be circularly polarized. Next. So this is the fabricated thing, fabricated antenna. Next. These are the electric fields from the antenna. This shows you the gain. Gain is about 8 dB, above 5 dB continuously, above 5 dB, and maximum gain is 8 dB that we saw. Uh, this again shows us the gain and the axial ratio. Axial ratio is below 3 dB over a good region. So circularly polarized and high gain that we realized. Next, where to use that? One application that comes to my mind is the aeroplane, usually the MiG. But in the MiG, they you must have seen the Republic Day parade in which the aeroplanes move in formation. Now, on those for formation, they require communication between each aeroplane as well as communication with the ground station. Now, for that, usually the antenna on the plane is on the tail. So that is called a tail antenna, tail of the antenna. But the radiation pattern gets distorted because when it is getting radiated in the forward direction, it is getting obstructed by the front of the aeroplane. So, as well as wing of the aeroplane, if you have antenna on the wing, they will also create problems. So, instead to avoid that, what we did is we put quad beam antennas on these aeroplanes. On these platforms, we put quad beam antennas for our simulation. We saw that we can have the radiation pattern in four different directions. So, one these will be communication between the aeroplanes in all directions as well as communication with the base station. So that is one of the applications. Next, then the next thing is to reduce the radar cross section. Why we want to reduce the radar cross section? Because if you are flying a plane or sending a missile to the enemy location, they will capture you by considering the radar cross section. Each plane, each structure electromagnetically has a particular radar cross section signature. And the more the reflection from the structure or the object, the easier it is to find out what object it is, how it is coming. To understand it more clearly, the objects are metallic objects. So the right hand side shows you a metallic plate from which we are getting reflections. So reflections are of high intensity. If you have a normal incidence, they are getting back in the normal backward direction with high intensity. Look at the left side what has happened. Instead of that surface, we have replaced that surface, or on that surface we have generated patterns for the uh, metasurface patterns. So since we have generated metasurface patterns, so now the reflected wave is in all directions, scattered in all directions. Now the total energy remaining same. When it gets scattered in all directions, what will be received will be minimum compared to the scattering in one direction where you receive it. Suppose in one direction you receive 5 watt, but you scatter it in 10 direction, you receive zero point 0.2 watt. So zero point 0.2 watt will be difficult to identify what is the surface. So with this principle, we design different surfaces which will reduce radar cross section. Next, this shows that was from the field point of view. This shows the same thing with radiation pattern. You can see the sharp radiation pattern for the perfect electric conductor top left. Then, if you have a linear distribution, the sharpness goes down, but it is sharp in one direction. But when you come to the random distribution of the elements, it is scattered in all directions. At different times, you will get different amount of energy. So you cannot determine what is the surface. Exact surface will be very difficult to find out. The signature, there will be no constant signature to determine what is the surface. Next, this shows the reduction of radar cross section measurement setup. So how to do the measurement? I think I will skip this because we have only 2 minutes more, 2 3 minutes. And this is from the measured results. The reduction in RCS reduction, you can see up from 20 to 10 dB, minimum 10 dB, maximum 20 dB reduction we have seen, and that can be achieved using random distribution of the unit cells on the surface. Next. Then there is this planar supercell configuration. In this, what we do is we consider three supercells. First is called the checkerboard or the chessboard type of distribution. Phase is 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0. So this way you have distributed in the first, second distribution you can see, and the third distribution also you can see. According to these phase distributions, the placement of elements are in the bottom row. Now with those placement, you can see what happens to the radar cross section next. Now you can see these are completely scattered. So if you go for that type of distribution, those type of distribution, complete scattering, there is no possibility of detecting the object. Next. This was the animation, so I'll skip this. No possibility of detecting any object in this. Next. And then I will stop with this one. There is another portion, but I will skip that. This we did using what we did is we were working on a cognitive radio antenna. So for that, we designed a broadband antenna, but we wanted to make it high gain circularly polarized antenna. So we have already seen, we have already discussed this high gain circularly polarized antenna. I will try to discuss it in more uh, elaborate manner here. So what we do is we take a dielectric substrate, look at the left side, top left side. We take a dielectric substrate, then on the bottom of the dielectric substrate, there is a feed line layer. On the top of that dielectric substrate, there is a ground plane. In the ground plane, we make a slot. So from the feed line through this slot, electromagnetic field will come out. Now above this slot, we put another dielectric substrate with these meta surfaces on the dielectric surface. These are called, then above that we will put another dielectric substrate with meta surfaces. So two dielectric surfaces above the antenna is the slot to below. So above that we put two dielectric surfaces. These dielectric surfaces are called PRS, partial reflecting surfaces. So from this surface, partial reflection will be towards the ground plane, which again will get completely reflected towards it, and most of the reflection will be towards the up in the upward direction or the vertical direction. Between these two dielectric surfaces in the above, the gap is such that it is working like a Fabry-Perot cavity. So Fabry-Perot cavity gain is enhanced naturally because of the Fabry-Perot cavity. You are getting more electromagnetic field there, confinement. Because of the confinement, the gain is enhanced. And high gain will be because these are partial reflecting surfaces, they will come out in the vertical direction. Above that, we use a polarization converter. If we use a polarization converter, the field coming out of the polarization converter will be circularly polarized with high gain. Next. This shows the simulated result and measured result. Axial ratio is below 3 or around 3. Mostly it is around 3. And we got good result from this. So with that, I will stop. Next. These vertices maybe sometimes else we'll discuss. Uh, with that, I will stop here. I appreciate your patience for being with me for the whole period and tolerating my cough and sneezing.
Thank you, sir. Now I request the participants to interact with the sir. If you have any query, you can ask. It's open for discussion. Dear participants, because
Yes, sir. Sir, actually, I have a question on gap between meta surface, sir. Sir, we are using patches for the meta surfaces. So the gap, how can we consider the gap, sir? Is it related to the operating frequency or wavelength or what, sir?
Yes, it is related to the operating frequency. What you have to do is find out Fabry plot principle, Fabry plot cavity. That cavity length is the gap. So look at
Okay,
any
sir.
our book on optics. There will be Fabry plot cavity. From the Fabry plot cavity, you can find out the formula for the Fabry plot cavity length. So that is your gap.
Okay, sir.
Any other participants? Priti, do you want to ask any questions? Priti? Devasi sir,
Uh,
ଆପଣ
sir, yeah, sir, thank you, Professor Mishra, for a nice talk. I mean, it's you covered a lot of areas. I don't know what to, but a simple thing I want to ask: how to measure this anomalous reflection? You have given a number. How you are measuring that?
Oh, for
Is
that
there any
you
procedure to measure?
yes, it is easy, very easy. You go use an anechoic chamber, put our antenna as the AUT antenna under test. Then use two antennas. One antenna you have to use as the illuminating antenna, one horn antenna. So that will be on a fixed time. Your antenna will be another antenna at any particular angle compared to your AUT. Put that antenna. That also will be a fixed time. Then you rotate your antenna. From rotating your antenna, you will find out the angle at which it is reflecting. So once you get the
Oh,
reflection, you know that. Simple reflection.
sir. Okay, thank you. Sir, then another question is, sir, how difficult to do it in the terahertz region, all this metamaterial?
No, what I will say is it is
Because there are a lot of
easier. It
research
is
going
easier.
on terahertz region.
As you go up in the frequency, it is actually easier.
Sir,
The theory becomes easier, fabrication becomes easier, everything is easier. Only thing is you should have that facility. If you have terahertz facility, it is much easier than the microwave
sir.
facility. There it is easier.
Oh, okay, sir. And sir, what about this cloaking, sir? Recently, I've seen these Chinese fellows. They have already constructed this cloaking device, totally invisible, sir. If you keep in front.
We also designed that in our laboratory at 10 gigahertz,
Okay,
at 10 gigahertz
sir.
microwave. We designed at 10 gigahertz microwave complete clocking. Ranjan, she
Okay,
designed complete clocking that we could do.
okay.
That is possible.
Sir, we,
Chinese, what you are saying is they are doing it at the optical frequency. So those people who are in the optical zone, those who are doing research in the optical
sir,
zone, they can use the same principle that we discussed. They can design the clocking. Complete invisibility is possible.
sir,
But problem is it is
sir.
only over a small being bandwidth. Bandwidth is very small.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Saubhagya sir, you have raised a hand. Please ask. Are you there, Saubhagya sir? Okay, you can ask. You unmute and ask.
Saubhagya, you can unmute yourself. Otherwise, Narayana, can you unmute him?
Okay, sir. Actually, we have given permission to unmute all. Sir, already.
Otherwise, you can write his question in the.
Sobhagya sir, you may write the question in the chat box so that I can read and sir will reply.
Sir, namaskar, sir.
Yes, Manjua.
Sir, namaskar.
Namaskar.
I, sir, I am very much thankful to your nice and informative talk. Just I am layman to this field. I have a simple question: how the optical plasma and electrical plasma differ from natural plasma?
Okay. Natural plasma is that you get in the atmosphere, ionosphere. There you get the plasma that is natural plasma, as far as
Okay, sir.
electromagnetism is considered. Now, when you bring that principle into optical zone or this microwave zone, lower frequencies or higher frequencies, there is a requirement of designing new structures which will behave like the natural plasma. As you know, natural plasma dielectric constant is 1 minus Fp square by F square. Andrew's formula.
Okay,
So
sir.
with that formula, one has to follow that formula. You have to design a substrate or design a material which follows that formula in the desired frequency range. 1 minus Fp square by F square, which means F is your operating frequency. In your operating frequency range, the structure should follow this formula. That I showed in the beginning.
Okay, sir.
Right? So you can use nano
Okay.
in optics. In optics, you can use nanowires. In microwave, you don't require nanowires for 1 mm or 0.5 mm. That will do. Right? So
Okay, sir.
that is
Okay.
the difference.
Okay,
Okay.
sir. Thank you. Thank you very much.
Thank you. So, my question is regarding extracting the equivalent circuit from the meta surface. How can how we can understand the inductive or resistive part or parallel or in series? Okay, it's very good question. So I give. Now, I have shown you one example. If you have understood that example properly, I took a split ring resonator, two split ring resonators actually, one split ring, the outer split ring, inside that there is another split ring. In that, we have on two sides two capacitances, two states. They represent two capacitances. So your circuit should have two capacitances. Now then you have a ring. Once you have a ring, you have a circular path of current. So once you find out, extract where there is a current path which is circular, that is your uh, inductance. So LC you have got. Then with L comes the uh, resistance because this is consisting of metals. So with L comes the resistance. So resistance and L will be in series, and the resistance will be there because of the metal that you are using. So that will be very small amount, but it will be there because of your metal that you are using. So from this, we have two capacitances which are parallel, two inductances which are parallel, but parallel inductances add together, so you can take one inductance instead of two inductance. You can take one inductance. Then with the inductor associated is always a resistor, therefore you have gotten a resistance. How to find out the resistance? You know the formula for resistance of a thin wire. So use that formula for the resistance for a thin wire. Find out the resistance. Then find out what is the radius of the ring. So circle, radius of the circle of the ring. From that you can find out what is the inductance. Then the gap. Gap gives you the capacitance. You can find out C is equal to epsilon A by D. So from that you can find out that D is the gap, A is the length of the slit. So from that you can find out the capacitance. So this is how, so depending on the structure, you have to apply your mind, do an analysis, and you can easily find out what is the equivalent circuit. I hope I am clear.
Okay. If there are no more questions, okay. So thank you very much, sir. Now I request Deepak sir to give vote of thanks. Deepak sir, over to you.
So, good afternoon, everyone. So, I'm happy to, I'm very delighted to give vote of thanks to Professor R.K. Mishra sir for his enlightening talk related to meta-electronics or meta-electromagnetics. So, he has covered multiple topics related to meta surface, meta materials, as well as different types of devices that can be synthesized using these concepts like uh, metasurface antennas or any type of clocking devices as well as RCS reduction. So various topics actually covered by Professor Mishra sir. So I hope it will be very helpful to all the audiences who are going to do some research in this field. So again, I extend my heartfelt thanks to all the participants also. So thank you, sir. Once again, thank you. And I hope in coming event, we'll definitely invite you for further discussion about this topic as well as new emerging topics. So thank you. Thank you, sir.
Sure.
Sir, now I request all the participants, please unmute your video. We can take a screenshot for today's talk.
Video.
Dear participants, please unmute your video. We can take a screenshot